Hello, and thank you for choosing to spend some of your time on this discussion of a topic that I haven't yet seen covered elsewhere. This is Using AI-Generated Code to Make GNU Radio Blocks, Part 1, provided by SDRS Wireless. We'll hear a little bit more about SDRS Wireless as well as the topic in a few minutes. If you are joining live, there will be time for some questions and answers when we get to the end of the talk and demonstration. Again, thanks for joining and glad to have you with us. I'm Carl Dietrich, and I work with SDRS Wireless, a consulting and training company focused on software-defined radio and related topics. I also work at Virginia Tech. I've been teaching SDR-related courses since 2006. I'm still learning and hope to share useful information, including some newer topics, as I learn them. Please visit SDRS Wireless online at any of the links below. Some disclaimers apply, so there's a link to those as well. This webinar and all associated resources that we provide fall under the category of video content for purposes of the disclaimers. Here's what we'll be covering. We'll aim to finish in under 30 minutes to allow time to watch this during a lunch break or two. First, we'll review goals. We'll briefly introduce SDR and GNU Radio for anyone who is not already familiar with both of them. We'll also address some questions such as, why would we use AI to make GNU radio blocks, and is it legal? Although, because we are not attorneys and are not qualified to give legal advice, these are more general thoughts with some links to articles that provide perspectives. Also, has what we're doing here been done before? And could you have learned to do it on your own? After that, we'll look at some example prompts and responses from two AI engines used to generate code for a GNU radio block, followed by some video that shows implementation and testing of a GNU radio block based on the AI-generated code. After that, we'll share some final thoughts. Real-time participants will be muted. However, there will be several minutes after the talk and demo to ask questions by chat. The question and answer session is not included in the recorded version. Goals or learning objectives for today are to learn to use AI to help us make GNU radio blocks, compare and contrast Python code output of two different AI engines, and then implement and test a GNU radio block that uses the AI-generated code. Along the way, we will learn an easy way to make a custom Python GNU radio block that is reusable in multiple flow graphs. Software-defined radio, or SDR, performs physical layer functions in programmable hardware and software. The goal is to gain some flexibility by having a radio in which you can just run different software to implement any kind of communication standard. And ideally, if the hardware is capable enough, that can even include new software that implements future standards yet to be developed at the time the SDR was designed and built. GNU Radio is an open source SDR project that provides a development toolkit and a runtime engine, and you can use this to develop your own SDR applications and run them on a variety of radio hardware or RF front ends that include analog to digital and digital to analog converters and some control capabilities, as well as a processor such as the one on your computer. GNU Radio has a project web page and a highly informative wiki at the links at the top GNU Radio bullet. And the wiki has some tutorials on it that you can refer to for many things that you might want to learn about GNU Radio. That said, we're going to do something here that I have not yet seen on the wiki, and we plan to have many more webinars that feature GNU Radio, but I would definitely consider that wiki a very useful resource, so I encourage you to check it out. Also, the GNU Radio project organizes an annual conference called GRCon, and many of the presentations from past GRCons are on YouTube, so you can look for those as well. Why use AI to make GNU radio blocks? Why would you do it? And is it legal? The main reason is that use of AI-generated code can speed development. However, you need some way to check the validity of the code or the accuracy of the code to ensure that the result has good quality and reliability. You will need to know something about the problem, the solution, including cases for which the solution is already known if there are any, the methods to be used, the programming language that the AI is using, and general programming logic as well as syntax to check the code for mistakes. At least ideally, you can inspect the code and make sure that it looks good and is doing what you asked for. At minimum, you need to be able to develop and run some test cases that show that the code is working properly under a variety of conditions. We'll do some of that today as time permits. If it is to be used in applications in which life, safety, property, or anything else important is at stake, the code would need to be inspected and tested very thoroughly. Legally, again, we're not attorneys and cannot provide legal advice, and also please refer to the disclaimers that we mentioned. We have included some examples of links to online sources that include a variety of perspectives. I suggest that you consult an attorney if you plan to sell or otherwise distribute AI-generated code. I found information about at least one lawsuit that may affect this situation. Personally, I expect that sources of AI-generated code that is unambiguously legal to use, license, and distribute will be available soon, even if one or more current AI engines are determined not to provide this. Meanwhile, you'll find some advice to developers to at least put comments in their code that show which parts of it were generated by AI, in case they need to go back later or review or replace those parts of the code at some point. The next question, has this been done before? Making GNU Radio blocks using AI-generated code. And yes, it has been. At least one student in a course that I co-taught last fall did use AI to generate code. This was encouraged as long as the students could show that they understood the AI-generated code, and at least one of the students did that successfully. And there could very well be multiple other instances of this. So this is definitely not the very first time a GNU Radio block has been developed that uses AI-generated code. However, I'm not sure that it's been taught in a well-publicized online format before. I haven't personally seen anything in several searches on the topic, so now there is at least one resource for learning how to do this. Along the lines of the comment about the policy about using AI in the course, I suggest that you check with your institution or employer before using AI to complete any type of assignment or product, and that you refrain from using any sensitive information, personal or otherwise, to prompt a publicly available AI engine. Now you might ask, could I just figure all of this out on my own? I'm confident that the answer is yes, because anyone with enough interest in the topic and resourcefulness to find a webinar like this has the ability, if not the time, to figure it out for themselves. So I'm mainly hoping that today's talk and demo will save some time for you and provide some assurance that you can use AI effectively and efficiently for this kind of work, at least to build relatively simple GNU Radio blocks. Please check back and also look for announcements of future seminars in which we plan to use and evaluate a similar development process with more complicated blocks. First, we'll look at an example of code generated by two different AI engines. The engine in Microsoft's Bing and Claude.ai. The prompt used to generate the code was approximately the same for each of the engines. Basically, show me some Python code for GNU Radio block to calculate peak to average power ratio in decibels for a complex valued signal. First, we'll see some video of the prompt entry and outputs from each AI engine. This takes about 90 seconds at double speed with a few edits. The overall process, including pasting code and text outputs into a document, took at most 5 minutes per AI engine. After we see what that looked like, we'll look at the outputs from Bing and Claude side by side, including the code, comments in the code, and other text output provided by each engine. Afterwards, we'll show an example of the process of making and testing a GNU Radio block that's based on the AI-generated code. We chose to make a block that calculates peak to average power ratio, or PAPR, for a complex signal. PAPR is commonly expressed in decibels, and you can see that Claude did this even though it wasn't told to provide the output in decibels. PAPR is of interest because popular signal formats that are used in cellular and Wi-Fi systems have some good features, but with these signals there's a large difference between the average power that's transmitted and the maximum power that must be transmitted, And when that ratio, PAPR, is high, that requires amplifiers that are rated for the maximum power, not just the average power, to prevent excessive distortion of the signal. So the higher the PAPR is, the more expensive the amplifiers are. PAPR is something that we might not monitor continually in an operational system, but PAPR limits how power and cost efficient a system that uses a particular signal format can be. Also, PAPR values are known for some common signals, so we can test a block based on either of these AI-generated code examples using those signals and see whether the results are accurate. Now we're going to switch over to a PDF file to see the code generated by the AI engines. The code produced by the Bing and Claude engines has a lot in common. Let's look at these different outputs. Both code examples import the Python library or package NumPy, which is a mathematical library, and it is common convention in Python to give packages an alias or nickname that you can use throughout the program that's briefer than the full package name. So these lines both do that using NP, which is a common abbreviation for NumPy. In each case, the next line imports a subset of the GNU Radio package, and this subset already has a brief name, GR. Both the Bing and Claude code outputs then start by declaring a class that has a name related to our application of calculating PAPR. The code also includes some comments, and what I've done is highlighted in yellow the parts that are common to both the Bing generated code and the code generated by Claude. In between, there's a comment that's in the code from Claude but not in the code from Bing that addresses what the block does, provides a brief description of the approach that it takes, and indicates that PAPR is expressed in dB. The comment also lists some parameters so that we're aware of those. There's also some code right here and here to initialize the GNU Radio block and give it a name, and then take in a signal using the np.complex64 data type. That's the Python data type that GNU Radio uses for complex valued data or in-phase and quadrature data. Then the output signal will be floating point. It'll just be a real number that is the ratio of two quantities, and we'll see how those are calculated. Each of the code examples gives us some information in the form of comments about how this is done. So here we have in the Bing code the power of the signal, and we calculate the peak power from that. We calculate the average power, and this will just be a vector of samples. And for each sample, we're going to calculate the magnitude or the square of that sample, and then calculate the peak power, which is just the maximum value of the resulting instantaneous power levels that are determined from this earlier line. And the average power will be the mean of the values in power, which is a vector of power levels sampled over time of a block of data. That's sent to this code through the GNU Radio block. So GNU Radio then sends data in packets or blocks of samples, and that's what we're doing here. We'll be taking in an array or a block of data and then processing it and outputting another block of data which has a single number in it, which is PAPR calculated over the incoming block of samples. You see some similar things over here in the Bing generated code, so it should be very similar. And here we're calculating the PAPR in dB. There's the calculation using 10 times log base 10 of the ratio of peak power to average power, and then it outputs that PAPR value by copying it over to the output signal array and by returning the length of the output array. And we see very similar things happening over here in the Claude generated code with a few more comments and a few more precautions. So this is just to avoid having a divide by zero error. The denominator, which could be 0, is updated by adding to it a very small number, 10 to the minus 10th. That's 0.1 billionths. So for practical purposes, it is 0, but for mathematical purposes, it keeps us from having an error if the average power happens to be 0. And again, we copy this to the output buffer. So this output array is set equal to the single value of PAPR underscore dB, and in both cases, that value is that ratio calculated for the most recently received block of input data. And again, we just tell how long that array is that we're passing to the next block as an output, and GNU Radio will take care of the rest. Both of these code examples came with some text and some comments. So I'll just give you an example of what the outputs were in this case. And there are some things that are a little different for one or the other of the engines. Bing, in some ways, is a little more verbose. It's pretty free with the exclamation points, so it seems encouraging and so forth. I'd say that Claude maybe doesn't sound as cheerful, but it is very informative, and it not only offers to add additional features, but gives you some examples or suggestions, and then they both give you some information on how to use the block of code. So you get a lot more than just the generated code, and you get a little bit of explanation about how to use the code and how the code works, perhaps a little bit of background. There's something about continuously calculating and outputting the PAPR in the Bing output, and you get kind of similar information from Claude, that it processes the complex valued input samples in Windows and outputs a stream of PAPR values. And there's something a little different in the Claude code, and that is a default Windows size that's mentioned in the comments as well. So there's a quick walkthrough of the outputs from each of the AI engines. Next, we will create a GNU Radio Python block, populate it with AI-generated code, and test it. To enable us to use the Python block in multiple flow graphs in the future, we will build a hierarchical block or higher block in GRC that will contain the Python block. Unlike Python blocks, hierarchical blocks can be reused within a GNU Radio installation. We'll look into porting the Python block to another GNU Radio installation in a future webinar or video. A higher block uses a pad source for each input data stream and a pad sink for each output data stream. The Python block processes data from the pad source and sends its output to the pad sink. To fill in the Python block, we keep but comment out most of the original example code from the Python block and copy in the code generated by Bing. We do use one part of the Claude generated code to ensure that the code never divides by zero. The code was generated outside the virtual machine where GNU Radio is installed, and copy and paste between the host operating system and the VM is not enabled. Because of this, and because the code is so brief, I simply read and typed the code. Once we have built the higher block and filled in the Python block, we need to generate it, and then reload the list of blocks. At this time, the higher block should appear under the GRC higher blocks category in the block list. Now we will build a flow graph that lets us use the PAPR and lets us see the PAPR that our AI-generated code produces so that we can test to ensure that the output is reasonable for some signals whose PAPR is known, and for other signals that are expected to have a PAPR that is higher, although for that case, we will not be comparing the calculated PAPR to an exact solution of the expected PAPR. Signals that we will use include a complex valued cosine function. This is essentially a complex exponential, which has a constant magnitude. Therefore, we expect the PAPR for this case to be 1, which is equal to 0 dB. We can see that the PAPR for each block of data, as shown in the Qt GUI number sync, is very close to 0. This result is reasonable. The next test will be to calculate PAPR for a real valued sinusoid. Here we will only use the real component of the sinusoid. Again, the peak to average power ratio is well known for this case and is equal to 2 or approximately 3 dB. We can see that the output values from our Python block are very close to 3 dB, so again, the result is reasonable. The next case is a sum of sinusoids at different frequencies, similar to the case of OFDM signals used in Wi-Fi and cellular communications. OFDM is known to have a high PAPR, although it is usually characterized as a cumulative distribution function, or CDF, rather than as a maximum value. Even without trying to generate a standard OFDM signal or referring to the statistics, we do see that the PAPR for our simple multi-carrier signal is higher than for the other signals. Here are a few conclusions from what we just saw. Both Bing and Claude can generate Python code for use in GNU Radio blocks. Their outputs are generally similar, although not identical to one another. You will want to visually inspect, test, and debug AI-generated code to help ensure its accuracy and robustness, as well as security. In this case, Claude provided code to prevent one potential error, yet missed an equally predictable potential error. However, Bing did not provide any error checking or workarounds to prevent errors. Both Bing and Claude provided comments in the code as well as text explanations and instructions. Text output from both engines was useful. In this case, Claude's non-code output was slightly more informative. We were able to make a working Python block using mostly the code from Bing with a small chunk of code from Claude that prevents one potential error, and we could have hard-coded or hand-coded additional fixes, features, and comments. This block provided accurate results for two well-known cases. Use of AI engines that are currently available for free to generate simple GNU Radio blocks saves some time and provides well-commented code. Time savings would probably be greater for more complicated blocks. However, in either case, we would need to ensure that we understand the code and also test it for accuracy. AI-generated code appears to be well-commented and explained, making it easier to understand. As already mentioned, we encourage you to consult an attorney, your employer, your school, and/or your instructor as needed, and to ensure that you take special care when developing code for any type of critical or important application or for a class assignment, and to avoid entering any sensitive information into an AI engine that you or your employer do not control. Again, it would also be advisable to consult any policies that may apply. Thank you again for your time and interest. If you are viewing the recording only, I hope to see you in a future real-time webinar or another video soon. For real-time participants, please send any questions by chat in the video meeting platform.